Now let us see what a successive approximation digital voltmeter is. So to start with, digital instrument is one which represents the measured value in the form of the digital numbers is known as a digital instrument. It works on the principle of quantization. The quantization is the process of converting the continuous input signal into a countable output signal. So, the instruments that are used to express the measuring quantity in numeric format is known as the digital instruments. Quantization is the process of Quantization is the basis of working of a digital instrument. It is an act of transforming an analog signal into its digital form. Digital instruments are composed of logic circuits that carry out measurement of the quantities. Due to several advantages of digital instruments such as high speed, the errorless results, the better resolution, and the greater accuracy over analog instruments, the popularity of digital instruments has increased rapidly. Also, digital instruments display the measured quantity in discrete numerals, thereby eliminating the parallax error and reducing the human errors associated with analog pointer instruments. In general, digital instruments have superior accuracy to analog pointer instruments, and many incorporate automatic polarity and range indication, which reduces operator training, the measurement error, and possible instrument damage through overload. In addition to these features, many digital instruments have an output facility enabling permanent records of measurements to be made automatically. The digital instrument basic circuits involve the use of logic gates and flip-flops. A logic gate is a circuit that produces a desired high or low output voltage when its several input terminals are all at the prescribed high or low input voltage level. Digital instruments are rapidly replacing the analog instruments because of their easy readability, better resolution, and higher accuracy. Digital instruments display the output in the numerical form, that is, in digital form. Digital instruments are used to measure the voltage, current, the power, frequency, etc. to enable digital instruments to recognize information inputs which are analog in nature must be converted to digital form. Hence, any digital instrument consists of an analog to digital converter in its input stages. The basic building of digital instrument is shown. So, in the basic building of digital instrument, it has A to D converter, a signal processing unit, and the display. Any digital instrument may consist of components like the resistors, the capacitors, the transistors, the linear ICs, the digital ICs, the display devices, analog to digital converter, digital to analog converters. The display block may be analog or digital in nature. If analog readout is required, the stage involving digital to analog conversion can be included before display. Next, the main advantages of the digital instruments over analog instruments are: they are superior to analog instruments because of high accuracy, smaller in size, low power consumption, high frequency range, detection of low level signals, high durability, good visual readout, and good quality, no human reading errors, no parallax errors. They have high input range with the automatic range selection and the overload indication. The input impedance is high, the resolution is better, the output in digital form can be directly recorded, and it is suitable for further processing with the development of IC chips. The cost, size, and power requirement of digital instruments are drastically reduced. So, there are a number of digital instruments. Few of them are the digital voltmeter, the digital multimeter, the ramp type voltmeter, the successive approximation type voltmeter, the dual slope voltmeter. Also, the other instruments are the digital frequency meter, the digital LCR meter, etc. Digital voltmeters are essentially analog to digital converters with digital displays to indicate the measured voltage. Digital multimeters are electronic volt-ohm millimeters with digital displays. Digital voltmeters are measuring instruments that convert analog voltage signals into digital or the numeric readout. The digital readout can be displayed on the front panel and also used as an electrical digital output signal. Any digital voltmeter is capable of measuring analog DC voltages. However, with appropriate signal conditioners preceding the input of the digital voltmeter, the quantities such as AC voltages, the resistances, the DC and AC currents, temperature and pressure can also be measured. The common element in all these signal conditioners is the DC voltage, which is proportional to the level of the unknown quantity being measured. This DC output is then measured by the digital voltmeter. DVMs have various features such as speed, automation, operation, and programmability. The DVM displays AC and DC voltages as discrete numbers rather than as a pointer on a continuous scale as in an analog voltmeter. A numerical readout is advantageous because of it reduces the human errors, it eliminates the parallax error, increases the reading speed, and often provides output in digital form suitable for further processing and recording. With the development of IC modules, the size, the power requirements, and the cost of DVMs have been reduced so that DVMs compete with analog voltmeters in portability and size. The digital voltmeters are classified mainly based on the technique. They are like ramp type digital voltmeter, the successive approximation type digital voltmeter, and the dual slope integrating type voltmeter. The ramp type voltmeter, the operating principle of ramp type DVM is based on the measurement of time that a linear ramp voltage takes to change from 0 volts to the level of the input voltage or to decrease the level of the input voltage to 0. This time period is measured with electronic time interval counter, and the count is displayed as the number of digits on an indicating tube or display. Basically, a ramp type DVM consists of a linear ramp which is positive going or negative going. The range of the ramp is plus or minus 12 volts, while the base range is plus or minus 10 volts. In this case, a negative ramp is selected. The operating principle and block diagram of a ramp shows that at the start of the measurement, a ramp voltage is initiated. The counter is reset to 0. The sample multivibrator gives a pulse which initiates the ramp generator. The ramp voltage is continuously compared with the voltage that is being measured. At the instant these two voltages become equal, a coincidence circuit generates a pulse which opens a gate. The input comparator generates a start pulse. The ramp continues until the second comparator circuit senses that the ramp has reached 0 value. The ground comparator sends a signal or the stop signal to stop the counter. The output pulse from this comparator closes the gate. The time duration of the gate opening is proportional to the input voltage value. The disadvantage of the ramp type voltmeter is large errors are possible when noise is superimposed on the input signal. So input filters are required for reduction of noise. So that is the basic principle on which a ramp voltmeter works. Now let us see the block diagram of the successive approximation type digital voltmeter. So successive approximation type digital voltmeter, it performs analog to digital conversion known as digitization. So here the block diagram of the successive approximation type of digital voltmeter is shown. So when the start pulse signal activates the circuit, the successive approximation register SAR is cleared. The output of the SAR is 00000000. That is from D0 to D7 shown in the figure. We get all zeros. So the output voltage of the D to A converter is also zeros. At the beginning of each measurement, a start pulse is applied to start-stop multivibrator. This sets 1 in the most significant bit of the control register and zeros in all other bits of the least significant. When the control register is 8-bit register, its reading would be 1 followed by 7 zeros. This initial setting of the register causes the output of the D to A converter to be half of the reference voltage, that is half of the capital V. If V reference is capital V, then the D to A converter output is half of the reference voltage. This converter output is compared to the unknown input voltage by the comparator. If the input voltage is greater than the converter reference voltage, the comparator output produces an output that causes the control register to retain one setting in its MSB, and the converter continues to supply its reference output voltage of half the V reference. The ring counter then advances by 1 count, shifting a 1 in the second MSB of the control register, and the reading becomes 11000000. This causes the D to A converter to increase its reference output by 1 increment to 1/4 volts, that is half V plus 1/4 V, and again it is compared with the unknown input. If the total reference voltage exceeds the unknown voltage, the comparator produces an output that causes the control register to reset its second MSB to 0. The converter output then returns to its previous value of 1/2 volt and awaits another input from the SAR. So, when the ring counter advances by 1, the third MSB is set to 1 and the converter output rises by the next increment of 1/2 volts plus 1/8 volts. The measurement cycle thus proceeds through a series of successive approximations. Finally, when the ring counter reaches its final count, the measurement cycle stops and the digital output of the control register represents the final approximation of the unknown input voltage. The control register connects the value of digital readout, which displays the digital reading of input signal voltage. So input signal voltage is equal to V reference by 2 plus V reference by 4 plus V reference by 8, so on, V reference by 256. So as we have seen, This is the block diagram of successive approximation type digital voltmeter. So here initially a start pulse triggers the start stop multivibrator. The multivibrator activates the ring counter which sets the MSB, that is bit D7 of the successive approximation register. The 8-bit digital word, that is 1 followed by 7 zeros of SAR, is converted into analog voltage by digital to analog converter Vout. Now this analog voltage Vout is compared with the input voltage Vin. If Vin is greater than Vout, the comparator output is positive during first clock pulse. The control circuit sets D7 to 1. If Vin is less than Vout, the comparator output is negative. The control circuit resets D7 to 0. Similarly, the bits beginning from D7 to D0 are set, reset and tested. So the measurement is completed in 8 clock pulses. So supposing the converter can measure a maximum of 5 volts, that is, the 5 volts corresponds to the maximum count of all ones, 8 ones. If test voltage Vin is 1 volt, the following steps will take place in measurement. So the first Vin is 1 volt, D7 is set, so 1 followed by 7 zeros. Compare, Vin is less than Vout, D7 is reset, the output voltage is 2.5. Next D6 is set, that is 0, 1 followed by 6 zeros. If Vin is less than Vout, D6 is reset, output is 1.25 volts. So this is repeated for 8 bits. Then you get the output voltage. So Vin is nearly equal to Vout, that is Vin is equal to 1 volt and Vout is 0.99785. This is how the successive approximation type voltmeter works. So all these operations, the comparison of the input voltage with the successive approximation register is completed within no time. So these are the various output levels for each bit. So 8-bit shows the voltage level very nearly equal to 1 volt. So we have seen we have a sample and hold circuit in the successive approximation type of voltmeter. So the input voltages other than DC, the input level changes during digitization and decisions made during conversion not consistent. To avoid this error, a sample and hold circuit is used. It is placed directly following the input attenuator and amplifier as you have seen in the block diagram. So in simplest form, the sample and hold circuit can be represented by a switch and a capacitor. So it is shown in this figure. It has a capacitor and a switch. So in sample mode, the switch is closed and the capacitor charges to the instantaneous value of the input voltage. In hold mode, the switch is open and the capacitor holds the voltage that it had at the instant the switch was open. So the output waveform of sample and hold circuit is in this way. So it holds the waveform. So if you see the advantages of successive approximation type voltmeter, the main advantage of this method is high speed measurement. It takes n clock pulses to produce an n-bit result. For example, 8-bit DVM, it takes 8 clock pulses to complete its operation. So this voltmeter is capable of producing nearly 1000 readings per second. So this is how a successive approximation type voltmeter works. As we have seen the circuit diagram, we have an input attenuator for various ranges, and the input voltage to be measured is connected to the input attenuator. Next, it is given to a sample and hold circuit. Next, there are two inputs to a comparator. The output of the sample and hold circuit is connected. And the next one is the D to A converter, which is nothing but the successive approximation converter. The comparator output is one of the input of the gate, and the other input of the gate is the start stop pulse through a delay circuit. So here we have a ring counter, the control register which generates the 8 bits to the D2A converter, the reference supply voltage, the control register once the input is equal to this approximated voltage, the control register's output is given to a digital readout. So to sum up, the successive approximation digital voltmeter performs analog to digital conversion known as digitization. When the start pulse signal activates the control circuit, the successive approximation register is cleared. The output of the SAR is 8 zeros. The output voltage of the D2A converter is 0 volts. At the beginning of each measurement, a start pulse is applied to a start-stop multivibrator, which sets 1 in the MSB of the control register and zeros in all other bits of the least significant bits to be zeros. When the control register is 8-bit register, its reading would be 1 followed by 7 zeros. This initial setting of the register causes the output of the D2A converter to be half of the reference voltage, that is half V. This converter output is compared to the unknown input by the comparator. If the input voltage is greater than the converter reference voltage, the comparator output produces an output that causes the control register to retain one setting in MSB, and the converter continues to supply its reference output voltage of half V reference. The ring counter then advances one count, shifting a 1 in the second MSB of the control register, and its reading becomes 1 1 followed with 6 zeros. This causes the D2A converter to increase its reference output by 1 increment to 1/4 volts, that is half volts plus 1/4 volt. And again it is compared with the unknown input signal. If the total reference voltage exceeds the unknown voltage, the comparator produces an output that causes the control register to reset its second MSB. The converter output then returns to its previous value of half volts and awaits another input from the SAR. When the ring counter advances by 1, the third MSB is set to 1 and the converter output rises by the next increment of half plus 1/8 V. The measurement cycle thus proceeds through a series of successive approximations. Finally, when the ring counter reaches its final count, the measurement cycle stops and the digital output of the control register represents the final approximation of the unknown input voltage. The control register connects the value to digital readout, which displays the digital reading of the input signal voltage, which is given as V reference by 2 plus V reference by 4 plus V reference by 8, so on up to V reference by 256. So here the advantages of the successive approximation type voltmeter is its high speed measurement, and it takes n clock pulses to produce an n bit result. This voltmeter is capable of producing 1000 readings per second. So the disadvantages of successive approximation digital voltmeter is the control circuit is a bit more complex in design and is costly. So to sum up, we have seen the successive approximation type digital voltmeter, construction, the operating principle, the working of the successive approximation type voltmeter, the advantages and the disadvantages. So this to specify a digital voltmeter, we have to specify different parameters like the display time, how many digits display it has, what is the input range of the voltage which we can measure, what is the accuracy, the resolution of the meter, input resistance, the input capacitance, what are the output signals, do we have the zero adjustment, do we have the overrange indication, what all it can measure, the functions. Next is, do we have a manual switching facility for selection? Next, what is a battery to be used in the voltmeter? The temperature across which we can use, the power on which it works, the size, weight and the polarity. So all these are the specifications of a digital voltmeter. Thank you.